Hello there, and welcome to this video on deductive reasoning. So our first video we looked at inductive reasoning, and now in this video we're going to look at deductive, and this is where we actually get to prove things. With inductive reasoning, you were just looking at examples and cases, and then you based your conjecture off of those. And a conjecture was just like your hypothesis of what was going on. So in deductive reasoning, some algebra is going to be used. So what we're going to do first is just practice some simplifying here with some algebra. And I encourage you guys to try to do these ones even before we go through them together if you want to pause it and try to go through them. So on the first one there, we got x plus 1 plus 2x plus 7 minus x minus 1. So when you ever have this minus here like that, that minus has to distribute into the brackets. So what this is actually going to equal, you're going to have x plus 1 plus that 2x plus 7, and then that minus is going to go with the x, so you got minus x, and then when the minus goes with the minus 1, those two minuses is going to give me a plus 1. So once I have that, now I can put my x's together. So I got 1x, another 2x's, and then I'm going to take away an x. So x plus 2x is 3x, and then take away an x, I'm at 2x's. So 2x. And then I'll put my numbers together, so plus 1 plus 7, so that's plus 8, plus another one, so we got plus 9. In the next one, we got x minus 2 squared minus 2x squared. So whenever you have something squared like that, what you're going to do is you're going to write it out twice. That way you're less likely to make a mistake, because what a lot of people think is they can just square the x and just square the 2, and that's not actually the case. It's close, but it's not quite right. And then we just had that minus 2x squared. So we're going to do our foiling. So we're going to have an x times an x, that's x squared. X times a negative 2, that's negative 2x. Negative 2 times x, that's another negative 2x. And then negative 2 times negative 2, that's positive 4. And then we still got that minus 2x squared. So simplifying this now, my x squareds, I got an x squared there, and then minus 2x squared there, so I have minus 1x squared. My x's I can put together, so that's minus 4x, and then I have that plus 4. So there's your final answer for that one. Looking at the next one, we got 60 plus 4, all divided by 2, and then subtract 2. So whenever you have something like this, what you should do is you should divide this by 2, and this by 2. You can't just do one or the other. It has to be both. So what I always do is I divide them both by 2. I break them up like this. So then that way I don't forget to divide them both by 2. And then simplifying the first one, 6 divided by 2 is just 3. So I got 3d. And then 4 divided by 2 is 2. And then minus 2. So these two are going to cancel out. So I'm just going to get 3d. And this last one here now, it says solve for x. So we just want to isolate and get x by itself. So x is being added with a z and a y, and it's also being divided by this 2. So we got to kind of undo those things. We got to do the opposite to get rid of them. So what I'm going to do first is I'm going to multiply this whole side by a 2, because that'll get rid of a divide by 2. And then I got to do it on this other side. So this 2 and this 2 are going to cancel out. So I'm going to have y plus z plus x equals 8. And then to get that x by itself, I'm just going to have to subtract a z, subtract a y, and then also do that on this side. And they'll cancel out on this side. So what I get is x equals 8 minus y minus z. So in this lesson, you're going to have to know things like this in order to do some of the questions. It's not hard algebra, but you don't want to make mistakes as you're going through. So back to our deductive reasoning. So in deductive reasoning, we're first going to look at some definitions. So looking at the first definition there, a proof. This is a mathematical argument showing that a statement is valid in all cases and there are no counterexamples. So there doesn't exist any counterexample out there that can disprove what you're trying to say, because you have literally proved it for all cases. Next we have generalization. So that is a principle, statement, or idea that has general application. So if something has general applications, this means you can apply it to more than one case or more than one scenario. And then finally we have deductive reasoning. So that is drawing a specific conclusion through logical reasoning by starting with general assumptions that are known to be valid, right? You can't start with an assumption that is false and then base your conclusions off of that, because everything that then follows that false assumption is going to also be false. So deductive reasoning is kind of opposite of what inductive reasoning was. Inductive started with something specific, like you looked at specific examples, say every day it rained when I was wearing blue shoes, and then you base your assumption off of that. You think every day if you wear blue shoes, it's gonna rain. Might not be true, but it's just based off your experience. And then deductive reasoning is the opposite. It's gonna go from general to specific. So you're gonna prove it generally, which means for all cases, and then any specific case you look at falls under that general case. So it is also going to be true for a specific case as well. And then the last definition there, we got the transitive property. We've seen this before when we did our sign law. So transitive property, it says if two quantities are equal to the same quantity, they are equal to each other. So an example of this would be if you had A equaling B, and you also knew that B equaled C, then you know, or this implies, that A must also equal C. So the way I try to remember this, I think it's transiting. It's kind of moving from one to the other. So A was equal to B, and B is equal to C. So A can transit all the way over. A also equals C. Next up here, we're going to look at our deductive reasoning. So it says that deductive reasoning is required to prove conjectures. Okay, the only way to actually prove something to be true, we need to use deductive reasoning. And often it involves algebra. That's why we did those examples there first, because if we can't do basic algebra, deductive reasoning is going to be a little bit more difficult. But it doesn't always use algebra. Sometimes there's examples where it might not. So it's often, but not always. Okay, so using deductive reasoning, what you're going to have to do is be very general. You can't use actual examples, so you can't pick like specific numbers. What you need to do is you need to be really general and use things like variables. So you could use like n. N could represent a number. And then if you had n minus 1, that's just the number right previous to it. And if you ever have trouble with this, just try some different examples. So if you had n, I'm going to replace that with a 3. So that's specific. That's not what you want to use for deductive, but I'm just kind of showing you. If you then took n minus 1, that would be 3 minus 1. And 3 minus 1, that's just 2. So you can see that that is just the previous number to 3. Looking at the next one, if you had n and n plus 1, those are consecutive. So that would be like 4 and 5. 2n is going to represent an even number, because if you have 2n, an even number is anything that is divisible by 2. So if I can divide this by 2, which I can, then it means it's an even number. And then lastly there, 2n plus 1, that's going to be an odd number, because if you have 2n, that was even, and then if you add 1 onto it, now it is odd. So these we are going to use lots in different examples. You're going to see them quite a bit. So just to reiterate again, deductive reasoning, you use this to prove something in all cases, whereas inductive reasoning before, that just gave you a conjecture which wasn't always true. It wasn't yet proven. So now we're going to move into some different examples here. So the first one, it says use a Venn diagram to make a valid conclusion about Shaggy. So it says all dogs are mammals, all mammals are vertebrates, and then lastly Shaggy is a dog. So for a Venn diagram, I don't care if you guys use circles or if you use rectangles, you just got to use some type of shape. So the first statement there, it says all dogs are mammals. So what I'm going to do is I'm going to draw a circle, and then I am going to label that circle. Anything inside of this circle is going to be a mammal. And from the first statement, I know that all dogs are mammals. So I'm going to make a category for dogs, and it has to be inside of mammals because all dogs are mammals. And then we'll call this dogs. So all dogs are contained within mammals. And then the second statement there, it said all mammals are vertebrates. So here's all my mammals, and all of those mammals have to be within vertebrates. So I got this bigger box here now, and I'm going to call this vertebrates. And if you're wondering what a vertebrate is, that is just any animal that has a spine. Okay, so we've looked at most of our information. Just the last thing now here is Shaggy is a dog. So if Shaggy is a dog, that means that we must place Shaggy within the dog category. So Shaggy has to be in here. Now from that, I can make some different conclusions from this. I can say that Shaggy is definitely a dog, they told me that, but Shaggy is also a mammal, and he also has to be a vertebrate because he is contained within both of those categories. So let's write that out. We can say Shaggy is a mammal and a vertebrate. Okay, so we've proven that, and with this one, we didn't even have to use any algebra. So not every question you're going to do is going to use algebra. The next one here, though, it says complete the following steps, and we're going to do it using inductive. That's the way we would have done it before, and then we're also going to do it deductively. So that's going to be actually proving it. So let's do inductive first. It says select a positive number. So I'm going to choose a 2. We'll start off easy. So triple the number. So 2 times 3, that's going to give me 6. And then next step, we're going to subtract 2. So I get down to 4. And then we're going to add 8. So adding 8, we get up to 12. Then we divide by 3. That gets me to 4. And then last thing, subtract the original number. So the original number was 2. So I'm going to go 4 minus 2, and I get out a 2. Okay, let's try it with another one. Let's maybe do it with a 5. So we're going to triple the number first. So I get 15, subtract 2, 13, add 8, get 21, divide by 3, get 7, subtract the first number, which was a 5. So 7 subtract 5, we get a 2. So I happen to get 2 again. Let's try it again. Maybe we'll choose here a double digit. Let's choose 10. So we're going to triple it, get to 30, subtract 2, get to 28. Then we're going to add 8. That'll get us to 36. Divide by 3. That is 12. And then subtract the original number. 12 subtract 10. We got 2. So what seems to be happening? Seems like every time we're getting out a 2. So using inductive reasoning, I would say based off these examples, these specific cases, I'm going to conjecture that every time you get a 2. I haven't proven it, but I'm conjecturing that that's going to be true. So now that we've done it inductively, let's do it deductively, and we'll see what happens. So select a positive number. So what I'm going to do, I'm going to choose n. N is going to represent my positive number. Triple that number. So I'm going to have 3 times n. That's just 3n. Next step, subtract 2. So I got 3n, subtract 2. Can't do any simplifying with that. Then it says we are going to add 8. So I got 3n minus 2. Add 8 onto that. This I can simplify. The negative 2 and the plus 8 I can put together and get a plus 6. Then we're going to divide by 3. So we got 3n plus a 6, all divided by 3. So remember when we were doing it in the very start, we said we got to divide each of those by that number. So 3n divided by 3 and 6 divided by 3. 3n divided by 3 is just n, and 6 divided by 3 is 2. Okay, so I got n plus 2, and then the last step was subtract the original number. So I have n plus 2, subtract the original number, which was a n, So the n and the minus n, those cancel out, and then I'm just left with a 2. Okay, so I've now proven deductively, so for all cases, no matter what number you choose, you're always going to get out a 2. So this deductive reasoning is really powerful because once you've proven it for all cases, you know that there can't be a counterexample. Whereas with inductive, sure, you've proven it for a few cases, but if I asked you to then try to provide a counterexample, it might be really, really hard to come up with one, especially if you can prove it that there actually isn't even one. So moving on to our next one here now. Number 3, it says prove that the sum of any two even integers is always even. So when we sum them up, remember sum means to add, any two even integers, we're going to get out another even number. And remember, whenever you guys see prove, for this, it means you're going to have to do it deductively. So you can't just choose some different numbers and add them up and try to prove it that way for a couple cases. You have to use deductive reasoning. Okay, so again, to reiterate that, you couldn't take two even integers like 2 plus 4, add those up and get 6 and say that this is even, so you've proved it. No, you've only proved that for one case, so you can't use that. So what we're going to do, first we're going to start off, because we need to come up with some even integers, and we need 2 of them. So what we're going to do is we're going to use 2 different letters, N and M, and they are going to represent integers. So that I here, that I represents integers. So to make these now even, like we did at the start, is if I can multiply it by 2, then I know it's going to be even. So I am going to take n and multiply it by 2, and I'm going to take m and multiply it by 2. So now that I have these two even numbers, what I needed to do was I needed to sum them. So I'm going to add these up. So 2n plus 2m. Now I have to try to prove that this is somehow going to always give me something out even. So what I could do, you could try to add these, but they're not like, I can't add them. They both have 2's, so let's try factoring a 2 out from both. So I factor out a 2, and I'm left with an n plus an m. So I got that. Now, to prove something was even, remember I said anything that is even is divisible by 2. So if I could take what I currently have, and if I could divide this by 2, which I can, 2 divided by 2 would cancel out, and you just get n plus m. If I can do that, I've proved that it is even. Okay, so the fact that it has this 2 here in front, a multiple of 2, that means that it is even. Okay, so that one didn't take much work actually to prove that. A lot of the time they're actually fairly simple. So looking at number 4 here now, it says prove that the product of an even integer and an odd integer is always even. So again, I got to come up with my numbers, and I'm going to need 2 because I need to use an even and an odd. So I'm going to say let n and m both be integers again. And this e, that just meant is an element of. We've seen that before. So I have to produce an even integer and an odd integer. So I know how to make an even one. I just times it by 2, so 2n. And for an odd integer, remember if I multiply by 2, it's even. And then if I add 1 onto it, now it is odd. So adding that 1 onto it makes it odd. So with these two numbers that I now have, what we were doing was we were going to take the product of them, and product is multiply. So I'm going to take this, and I'm going to multiply by this. And I want to prove that this is even. And again, even means it's divisible by 2. So let's simplify what we have here and see what we get. So we're going to have 2n times 2m. That's going to be 4nm. And then we got 2n times a 1. That's just going to equal a 2n. And now looking at that, what I want to try to do is factor out a 2 so that I can see it's divisible by 2. So I'll factor out a 2. That's going to give me 2nm. And then with the second one, if I factor out a 2, we just have an n. And now because it has this 2 here in front, remember, that means it's going to be divisible by 2. And therefore, it is even. So that was our last example. We just got our textbook questions now here at the bottom. And then one last thing, for you guys' textbook questions, you're going to have to know what the word median means. Another word that kind of represents median is middle. So if you were trying to find the middle of something, what you want to do, if you had, say, a bunch of terms, you're going to count inward from both sides the same amount, and then that will get you to the middle. Now, if there is, say, like 2 terms and you hop into the middle, and then you can't hop to the very, very middle, what you do is you just take the average of these 2 terms here.